Local lakes are rising fast. I checked the numbers for Lake Oroville. This morning, Lake Oroville is at 789 feet elevation. This is the Feather River near Lake Oroville. The lake is up 23 feet in just 3 days.
1 minute ago, deep inside California's water monitoring network, a number appeared that engineers are trained to question before they believe. There was no storm moving across the Sierra Nevada, no emergency release from upstream reservoirs, no seismic event strong enough to trigger alarms. And yet, Lake Oroville was rising. At first, the change was small, easy to dismiss as sensor noise. But then, another reading arrived, and another, each one higher than the last. Within hours, the trend was impossible to ignore. This was not seasonal snowmelt. This was not runoff. This was not how a reservoir behaves in the middle of the night. By dawn, the lake had surged more than 23 feet. For a system that protects millions of people downstream, every single foot matters. 23 feet does not signal recovery. It signals force. It signals a system being pushed faster than it was ever designed to move. Inside control rooms, engineers stopped asking when the rain would come. They started asking where the water was coming from. Because when a reservoir fills without weather, without warning, and without precedent, it isn't just a measurement that's wrong. It's the assumptions beneath it. And in California, when assumptions fail, consequences follow. This is the story of the night Lake Oroville behaved in a way no model could explain, and why what happened next forced the state to confront a danger it thought it had already survived. Chapter 1. 23 feet in the dark. The first abnormal reading appeared shortly after 2 a.m. Inside a quiet control room miles away from the dam, a monitoring station anchored along Lake Oroville's eastern basin transmitted a data point that immediately stood out. The water level had risen, not dramatically, but just enough to fall outside the range of normal overnight fluctuation. At first, it didn't trigger alarms. Small overnight changes happen. Wind can push water. Temperature shifts can affect surface readings. Engineers are trained to distrust a single data point, but this wasn't a single data point. Minutes later, another reading arrived, higher than the last. Then another, and another. Within the hour, the increase exceeded what should have taken days, not minutes. By 3:30 a.m., the lake had already climbed several feet. Still, there was no storm on radar, no rainfall upstream, no scheduled releases from connected facilities. Every system that should explain the rise showed nothing out of the ordinary. That's when concern quietly replaced curiosity. Redundant sensors were checked. Backup gauges confirmed the same trend. Automated systems were cross-referenced with manual benchmarks. Nothing disagreed. The lake was rising, steadily, relentlessly, through the night. By sunrise, the numbers crossed into territory no one in the room had seen before. More than 23 feet. To the public, that number might sound abstract. To engineers, it represents an extraordinary volume of water, billions of gallons entering a system that had not been prepared to receive them. And the speed was the most troubling part. Reservoirs are designed to rise gradually. Operators depend on time. Time to adjust releases. Time to warn downstream communities. Time to evaluate stress on infrastructure. That time didn't exist. As daylight reached the shoreline, field teams were dispatched immediately. What they found removed any remaining doubt. Water lines had advanced far beyond previous markers. Floating buoys sat higher and farther inland than mapped positions. Access roads used just days earlier now disappeared beneath rippling water. This was not an error. The lake itself was confirming the data. By mid-morning, the conversation inside operations centers shifted again. The question was no longer whether Lake Oroville had risen, it was how. Because without rainfall, without upstream input, and without mechanical releases, the reservoir had gained an amount of water that should have been impossible. And when water moves without a visible source, it forces a far more unsettling possibility, that the system is being fed from somewhere no one is watching. By the end of the morning briefing, one thing was clear. Whatever had happened overnight was not finished being understood, and the implications extended far beyond the shoreline. Lake Oroville had changed, and California was about to feel it. Chapter 2. Eliminating the impossible standard protocol demanded every known explanation be ruled out. Weather radar showed clear skies across the Feather River watershed for 3 straight days. River stages downstream remained flat. Satellite imagery revealed no debris inflows or landslide scars. Seismic monitors showed no slope collapse signatures. One by one, the usual suspects were crossed off the list. Still, the water climbed. When field teams reached the shoreline after sunrise, they saw physical proof. Water lines had advanced far inland. Buoys sat in the wrong locations. Structures that should have been well above the surface now met incoming waves. This was not sensor drift. Something real and powerful had altered the reservoir overnight. Chapter 3. Why Oroville Terrifies California. Lake Oroville is not just another reservoir. It anchors the California State Water Project, supplying water to more than 27 million people, supporting vast agricultural districts, and generating hydroelectric power for hundreds of thousands of homes. Every foot of elevation represents billions of gallons and billions of dollars. When Oroville behaves unexpectedly, the consequences ripple across the entire state, and the memory of 2017 still looms large. That year, structural damage to the main spillway triggered the largest dam-related evacuation in U.S. history. Nearly 200,000 residents fled downstream communities amid fears of catastrophic failure. The dam survived, but trust never fully recovered. So when unexplained water movement appeared again, fear spread faster than any official statement. Chapter 4. The water that didn't come from the sky. Within hours, the investigation took a sharp turn. Laboratory results from shoreline water samples revealed something deeply unsettling. The chemical makeup didn't match surface runoff. Trace elements appeared in concentrations typically found only in deep groundwater systems. Isotope ratios fell outside the range associated with Sierra snowmelt. Mineral signatures suggested prolonged contact with heated bedrock far below the surface. This water hadn't arrived from above. It had come from below. Geophysicists reviewed microseismic data and found clusters of small earthquakes beneath the reservoir, too minor to feel, but precisely timed with the rise. Fault structures mapped decades earlier suddenly became relevant again. The theory forming inside closed rooms was one few wanted to say aloud. A subsurface pathway may have opened, allowing pressurized groundwater to force its way into the lake. If true, the source might not be limited. Chapter 5. The worst-case alternative. Another possibility frightened engineers even more. Internal erosion. Known as piping, it begins invisibly. Water carves a path through dam materials, removing fine particles until pressure forces accelerate the process. By the time surface signs appear, failure can be imminent. Drainage systems within Oroville Dam showed subtle anomalies. Pressure readings shifted. Turbidity increased in places it hadn't since the last crisis. The pattern was disturbingly familiar. History offered grim reminders, from Idaho's Teton Dam to failures in Central Asia and Europe. In every case, early warning signs were present. In many, hesitation proved fatal. Independent experts were called in. Additional testing ordered. Acoustic instruments deployed to search for hidden inflows. The answers would take time. The lake did not wait. Chapter 6. People, pressure, and the cost of delay. Along the shoreline, residents noticed the change before officials spoke publicly. Docks vanished. Roads softened. Water crept toward homes that had survived years of drought. Families who once evacuated in the night quietly began packing again, not waiting for instructions this time. Downstream, environmental sensors registered stress. Sediment moved. Water chemistry shifted. Treatment facilities adjusted processes on the fly. Behind the scenes, tensions grew. Some agencies favored a geological explanation, one that shifted responsibility away from infrastructure. Others feared the implications of structural compromise. The debate was no longer just scientific. It was political, financial, existential, because if the warning signs were real and ignored, the cost would be measured in lives. Outro, the question that remains. What is certain is this: Lake Oroville rose 23 feet overnight, without rain, without releases, and without precedent. The chemistry points downward. The sensors show pressure. The history offers no comfort. What remains unknown is whether the source will stop, or whether this was only the beginning. California's water system was built for predictability. The climate no longer offers it, and as the lake holds its breath, so does the state, because the most dangerous failures are not the ones we see coming, but the ones we hesitate to believe. Subscribe for verified, science-driven updates on California's evolving water crisis before the next warning arrives.